light capture area. Think about this aperture. So let's take a few minutes, a minute or so, and think about this particular situation. Is there anything you can do to increase the gain? And we had a nice exercise last time, so I want you guys to do the same thing. Think about this situation. Is there anything you can do? And you can discuss. Feel free to talk. You can discuss it behind you if you want. You have to start with simple systems. That's why I want you to think about this first. Any ideas?
Well, I was thinking if your pot is right in the middle that you're trying to cook, you could focus everything right onto it.
So you're saying increase the, you mean design the reflectors to be focusing rather than into some parts further away like this? Yes, that's a good point. The caveat there, which we will talk about, is that means you have to be very precise at tracking the sun. Okay, this is referred to as the acceptance angle. We'll talk about this, and this is dictated by the second law of thermodynamics. So how precisely you concentrate the light is inversely proportional to how precisely you have to track the sun. That's a good point. That's one way to increase it. Anything else?
I think just in your selection of materials, because I remember as a kid making one of these out of foil, and obviously that's reflected.
Yes.
There are other materials that are.
Absolutely, yeah. So the biggest loss here, in a sense, would be the reflection losses of this. Right? If this is 99% efficient, that means you lost 1% of the light right there. Right? But typically aluminum, for instance, is maybe 60, 70%. So you're losing quite a bit. That's a good point. You can use better material. Anything else?
To increase the size of the reflectors?
Yes. That's actually that's the most common sense things. You could just keep going bigger and bigger and bigger and bigger. That's what common sense would dictate, but turns out that's not actually possible. And we'll also talk about that. And there's a reason for this. I mean, you can imagine the reason for it again comes from the second law of thermodynamics, because if there is no limitation, I could just keep going more and more, and I can have infinite concentration, right? I can concentrate light as much as I want. It's not possible. Again, dictated by the second law of thermodynamics. And we'll talk about all this later on. Is there anything else? But you can go more than what I'm showing here, obviously. And you, of course, you can do other shapes, right? This is just showing a straight line. You can do a parabola, you can do other things, right? Anything else? Why can't you put a lens on the top to do what you were talking about? A Fresnel lens like we saw in the last lecture. Right? You can do all kinds of things like that. Okay, I mean, it's fine, but just, yeah, I think we exhausted all possibilities, at least what I can think of. But anyway, okay. So then the next thing is the losses. So as I told you that we'll talk about losses. So in heat systems, of course, losses are dictated by three things: conduction, radiation, and convection. Conduction is simple. Anything that touches the hot thing obviously takes heat away from it. So you want to make sure that wherever you're trying to increase the heat, you want to make it insulated from the surroundings, right? Radiation refers to energy that's radiated out by thermal radiation, electromagnetic waves, photons, right? And that's an important loss of heat, particularly, for instance, although the enclosure is really hot, in case this insulator is not very good, you will start heating up the outside, which means that the outside now behaves as the black body will start losing heat, right? That's an example of a radiated loss. You can also have convection. Convection refers to heat essentially being transferred in gases, right? Air, plasma in general, but air is what we typically talk about. So the example there is pretty simple. So this thing is very hot. the air molecules will start circulating here. As soon as it touches, the air molecules touch this hot object, will gain some of the heat and start moving away. So it will start convecting away. And of course, because the other surfaces are relatively colder, it will transfer the heat to the other surfaces, and then they can lose heat by radiation. So although it's an open system, obviously, right? So we have to be very careful about how we design systems based on what we are trying to achieve clearly. So in this particular case, one can use make sure the absorber plate, which is this thing right here, is insulated from the bottom of the cooker, so there's no conduction here. The radiant heat, longer wavelengths are trapped by the container by proper choice of this transparent material, whether it's glass, foil, whatever. Heated air may leak through gaps, doors, etc. by convection as well as the combination of convection and conduction that I talked about earlier. So relatively simple things, but important to keep an eye on these. Heat storage. This means essentially how much energy does it take to increase the temperature of whatever object you're trying to increase temperature by 1 degree. This is referred to as heat capacity. Okay? So intuitively what it means is, it's the ability to retain heat. In other words, let's say you cook something and you put it back in the shade, how long will it stay hot? Okay? So it's related to not just heat capacity but also velocity, but heat capacity means that if you have large heat capacity like water, for instance, it can retain the heat for a very long time, as long as you have good insulation and things like that. So, but higher thermal mass means that it takes longer to heat up as well, which means those are the trade-offs. So if you want something which you want very quickly, then you want low heat capacity, but then it may not last very long after the sun's gone behind the clouds or whatever. So obviously interesting trade-offs here. You can see the design of the material here. If you're careful, you would really want the thermal mass to be high inside and have insulating material on the outside. So there are some interesting thoughts that can go into this. Okay, now let's talk a little bit about the materials. Well, what are the different ways to think about materials? Again, the whole purpose of this exercise is not necessarily to understand in detail the solar cookers, because it's a very simple system, but is to have this exercise of what are the different things we should start thinking about when we design new systems. Okay, that's the key concept I want you to gain from this whole exercise. Okay, so again, just looking at this very simple setup. So you have insulation on the outside. You have a tray. You have some airspace separating the tray from the bottom with some spacers here. You can have reflective surfaces in the inside to trap more of the heat, because the light then bounces around more times, which becomes very important. We'll talk about this in solar cells later on. You have a reflector out there, moisture-resistant coating, because you might be cooking something that generates humidity, and that can corrode surfaces, obviously, so you have to be careful with that. You want structural materials, and of course you have the glass or plastic window up here. So the key things, of course, structural materials. You can use wood, cardboard, metals, bamboo, bricks, stone, plastic, rattan, etc. Of course, the trade-offs are obvious: heavy, rigid, long-lasting versus light, cheap, simple. Right. Same thing goes for all these different sections. Insulation, it can be aluminum foil, down for the cellulose, rice hulls, wool, etc. Obviously, it goes with where it's available, how expensive it is, and so on. Transparent material, glass is relatively expensive for these things because it's brittle, it can break. High-temperature plastics like oven roasted bags. For moisture resistance, inner walls must protect the rest of the cooker from the moisture, as I mentioned before, and that turns out to be a much harder problem, as you can imagine, right? So there are several polymers that can be used. Some of them are relatively cheap, like PET or the things used for plastic bags, like polyethylene, versions of polyethylene. So, I mean, of course, there are also other design considerations that we touched upon in the last class, which we don't necessarily think about from a traditional engineering point of view. The size, how appropriate is it for the amount of food? Portability needs cookware accommodation, where certain kinds of material, cooking utensils can fit in it. Sunlight collection area, larger collection area, of course, higher temperature, as well as the heat loss not increase, as we talked about. proportion. Okay, so this is some questions here, just to think about ourselves. Is a square box better than a rectangular box? The question, of course, depends upon where you put the reflectors and so on as well, but any ideas, thoughts? And why are we even considering this? Or does it not matter?
Well, it matters because if one is more efficient or better at doing solar cooking, that's the one we want to use.
Yes.
But I don't know.
Why? Yeah.
About it.
Yeah, that's my question. Yeah. Is one more efficient than the other, or is there any reason to even think about it?
I would think maybe square because it would be easier to heat spread a little more evenly.
Okay, that's a good point. Yes. Yeah, that's a valid point. But I'm thinking of something slightly different. What about the sun? What does the sun do? It moves, right? So you have a swath of sunlight over several hours. Does it look like a square? Looks more elongated in one direction, and we treat this as what's called a degenerate direction, right? The direction which the sun moves. So you can imagine, it depends on the design. So I'd say there are caveats here. You can imagine a situation where you make it longer in the direction of the motion of the sun and have some concentration in the other direction, then you don't need to track the sun so much because it stays with the color. But you have the problem that you pointed out of uniformity. Okay, so it's an interesting idea, and it's worthwhile thinking about it. I'm not saying I have all the answers. I'm saying it's important to think about things that you don't typically think about. That's it. Which direction should the rectangular box be oriented? Of course, in the direction such that the long axis coincides with the motion of the sun. Right? That's what you would do. Is tracking required? Yes, typically yes, as we saw in some of the videos in the last class. But sometimes you can avoid some of this if you do things like making it long in what's referred to as the degenerate direction of the sun. But we'll talk more about examples along these lines later on. Tracking the sun is a very, very important and very difficult and expensive topic. So we'll kind of come back to it again. So the last thing to think about is, okay, you built the best possible solar cooker. It's cheap, it worked great. Then it fails in the market, and you get it out there. And there are many reasons why this can happen. And it has happened in the past, and I'm just giving examples from what I've found in the literature. Obviously, things taste of food. Maybe just the way you cook is different than culturally what people are used to. Temperature control is not there, which we talked about last class. What happens on cloudy days? Is it useless? Cost, of course, and disrupting traditional gender roles because, for instance, it might be so fast to cook that the women in a village who are traditionally don't have the time to do anything else now have a lot of time. So it creates really interesting social dynamics. And that's happened in some places in Africa. So I mentioned these because these are all interesting things that you don't necessarily think about as a technologist, but it's very important to think about. And the lesson that I want you to kind of start thinking, is that when we strive to solve a problem, which is what we are trying to do as engineers, we should really try to walk in the steps of people you're trying to solve the problem for. And the only way to do that is to talk to people like that. So you get feedback. And try to understand what things could go wrong. And those could be nothing to do with technology. Or it might have everything to do with technology, but you haven't thought about it. Right? So that's kind of, I would say, one of the lessons of what I'm trying to convey here. Certainly lots of opportunities with technologists as new market opportunities, fuel price rise. Are there interesting things we can do with technologies combined with microcredit, which I assume some of you are aware of, which is very popular nowadays. Can we incorporate solar cooking into home designs? So anyway, these are just some thoughts. Keep in mind. Okay, so just a short step to the next lecture, because this was from last class. Just to remind yourself, we will have mentors for your presentations, particularly for the commercialization part of it, in the second part of the semester. Just make sure that the key reason, and you'll only meet, I only require you to meet with them twice during the semester, about an hour or so. And the main reason is for you to practice your presentations and make it cleaner, and also get feedback on the business canvas and commercialization plan and so on. And they're very, very helpful, and have a lot of experiences, so take advantage of this opportunity. So I have right now, and you can see this on the schedule, 1 hour each in November 4th, the week of November 14th and 28th. And like I said, I'm flexible, so you can move things around, of course. And you need to coordinate with the mentor yourselves through your team. I can help, of course, so you can just email me. Related to this, it's important that those of you who are interested in giving me some input for how I should assign teams, make sure you let me know. I know many of you have already did. Let me know what you're interested in, or if you have certain skills that you want me to take into consideration when I assign teams. Again, I'm trying to assign the teams next week, so end of next week, let's say, something like that. So let's continue. So the lecture today was to cover essentially some overview of a series of projects, potential projects, and give you an idea of the different challenges which might be involved in each of them from my perspective. Now, it could be very different from your perspective, and hopefully it is, and you're thinking of this and of solutions in a very different way. That's my hope. So first, the problem I first chose was solar water pasteurization, and it's an interesting problem, and very, very important problem. Something like 1 out of 6 people on the planet have no access to clean drinking water, and it is only getting worse. So it is going to be a huge, very important problem. Half the hospital beds in the world are filled with people suffering from water-related diseases. 80% of deaths in children are due to contaminated water. So it's a big problem, obviously, and a big opportunity from an engineering point of view, right? This is a big problem we can try to solve. Now, what can we do about it? So the solutions are straightforward. If you heat water to something like 149 degrees Fahrenheit, 65 degrees Celsius, it pasteurizes water, which means that it makes it safe for us to drink. It kills something like 99.999% of bacteria, something like that. The key point here is there's no need to boil the water, okay? Which is great because boiling water requires a lot of energy, right? If you can do it with not boiling the water, that's a really good news. Pasteurization is the use of moderate heat to kill disease microbes, and we all know milk is pasteurized. It's about 31 degrees Celsius for 15 seconds. So anyway, so 65 degrees Celsius for 60 seconds is all we really need. So before I go into it, is there any problem with this good news that anyone can identify? Just from common sense. I said it's a good news that you don't need to boil the water. You only need to do 65. What is the problem with that? Yes, of course, you need the energy to do it. That's right.
You need to make sure it uniformly reaches that temperature.
Yes, that's also very important. So, fortunately, water is certainly relatively easy to do it because it's not super conductive, but at least it's a good point because you don't want hot spots. You're right. I'm wrong. Yeah, you need getting into uniformness. Anything else?
Don't you still need to remove the contaminants that are inside, like the oil?
That's a good point. Here we are assuming that it has already been filtered out. All the, let's say, gross contaminants have been filtered out. So we're talking about microbes here. This is where water pasteurization comes in. So it's kind of the last step. But you're right. It's a good point. Anything else?
The things in the water other than microbes?
Yeah.
Pollutants?
Sorry?
Like pollutants?
Yeah,
Will
like.
be killed by the temperature?
Yeah, well, most organic toxins to human beings, not inorganic. Organic toxins will be killed. Now, if you were raising an important point, if there are inorganic lead or mercury or something, no, that's a very different problem to solve. But this is still an important problem because vast water sources are essentially contaminated by bacteria because of livestock and things like that. Not really by heavy metals because you don't have industry, right? But it's a good point, very good point. But the most important problem, and I did not realize this until I read it, so it's okay, is the fact that how do you know that the water has reached 65 degrees Celsius? You just don't know. right? And it didn't occur to me, obviously you don't know. So if you look at water, I mean, you can't feel and say, right? You can't. So that is a very, very big problem, right? It's a simple solution, but it's a huge problem which as engineers we don't typically think about. So the most important advance that someone came up with is an indicator, a cheap indicator that tells you that the water is at 65 Celsius. So let's see what that is. Okay, they call this a water pasteurization indicator, WAPI. It's essentially a wax that melts at 65 degrees.
The WAPI, or water pasteurization indicator, is a simple device that indicates when water has been fully pasteurized. A plastic vial with the wax on the top and the washer on the bottom is placed in the middle of the pan. When water is heated to the pasteurization point, the wax melts and drains to the bottom of the vial. When cooled, the wax hardens again, and the WAPI can be turned over and reused again and again.
Okay, so that's very important problem, very simple solution. Right? It's a good example of innovation in my opinion. Okay, so what other technologies exist? So that was the indication problem. Now, how do we actually heat up the water? That's the more important problem that we are here to solve to some extent, right? What other technologies exist? Obviously, you can use a solar cooker. So we saw one of these box. I forget what it's called. Anyway, foldable flat-based cookers where you can just put a black container with water, heat up. Or you can have a custom device that traps the heat. It's don't actually remember what this is, but you can take a quick look in a couple of seconds.
Exposed to biological pathogens in the water.
Just fast forward it.
The aquapack uses solar energy to kill these pathogens using the proven process of heat pasteurization. Simply fill the aquapack with up to 4 liters of water, place in direct sunlight, and observe the orange water pasteurization indicator. After a few hours, the orange color disappears, indicating the pasteurization temperature has been reached and the water is safe to drink. The aquapack can be inexpensively manufactured in developing countries for about $2 each, providing both jobs and safe drinking water.
Okay, so that's again an interesting solution because it talks about two things, right? One is a very simple solution in the sense that it can actually be implemented locally, so someone locally can actually make it. And the other thing is that it is fairly robust. There's nothing complicated there. It can last, and they solve the indicator problem as well that we talked about. Simple. Of course, the simplest possible solution is this, which I found. Basically, leave the water for several hours in a PET bottle, which is available everywhere, and you get what they refer to as solar water disinfection. So this, or UV rays kill most of the bacteria. So it's a combination of both temperature and the fact that sun has plenty of UV rays, which causes skin cancer, but let's take advantage of it in this particular case. So I don't know if there's anything new here.
Promoting self-sufficiency and spreading sensible green solutions worldwide.
No, there's nothing here. Sorry, I don't remember. So, but anyway, it's a simple idea. So you can think about this as again, I started with the point that this is an incredibly difficult, incredibly big problem, right? Now think about it. 1 in 6 people on the planet have this problem, and it's only going to worsen. And there are simple solutions out there. So think about, as an engineer, what's really interesting, and what I would like you guys to think and you all to think about is there anything we can do to innovate, either optics or materials, we can make this better? Because that can impact a huge number of people, right? We're talking about 4 billion people, right? And potentially make a lot of money as well, obviously. The second problem, so that's one problem, solar water pasteurization. The second thing I'm talking about is solar water desalination, which is usually it's a step which comes before, but you can combine the pasteurization, desalination, obviously. Desalination does not mean you get rid of oils and pollutants, but it generally means you take water from the ocean and get fresh water. And as you probably know, I don't know if you are aware of this, but solar water desalination is slowly becoming a very important source of water in the Southwest, particularly in California, because, for instance, in Southern California, Bill is just commissioning the largest water desalination plant in the world. I think in the world, or maybe the second one, I forget. but it's becoming an incredibly important resource because, as we know, snowpack's reducing and we don't have enough water in the Colorado River to share among all the people. Same thing is happening in Israel, Saudi Arabia, I would say many places in Africa, certainly, on the west coast. So the key point here is that what's very interesting is that if you look at the map of the world, you have this really interesting coincidence between the resource scarcity of water and the fact that you have huge solar resources everywhere in the center of the world. We have, where we are, for instance, we have water scarcity and we have huge sunlight resources, right? So is there anything we can do? So to me, it looks like it's an obvious thing that we should start thinking about using the sun to try to solve this problem to some extent, right? So let's think about that, what exists today. So desalination, of course, happens naturally in the world. What we talk about the hydrologic cycle. Very simple, right? We all learned this in high school. We have water from the ocean, gets evaporated by the sun, forms clouds, comes onto land, and when it evaporates, you're leaving the salts behind, which is why the ocean is salty, and that's desalination, and then it comes down and get fresh water, right? And this whole cycle repeats. Our goal here is to do the cycle in a manner that's much faster and hopefully more efficient than the way it's done naturally. Although we'll see some solutions are not necessarily that efficient. The most common artificial method of desalination is refers to as reverse osmosis. So almost all the plants, the largest one, I think, there's one in Israel, Mexico, and the one in San Diego, near in Southern California. I think those are the largest two. All of them use reverse osmosis. And I'm pretty sure the one in Saudi Arabia as well. So what's reverse osmosis? First of all, osmosis. If you take two beakers, let's say, which are connected, at one side you have pure water, and the other side you have salt water, and they're separated by a membrane that allows allows water molecules to pass through, but it will prevent salt from passing through. Okay, what will happen? We know from our high school chemistry that diffusion will happen from regions of high concentration to low concentration. And a good analogy for those of you who might have forgotten is if you spray a perfume on one corner of the room and you give it enough time, it'll spread all over the room and you'll smell it everywhere. And that's diffusion. Because where you started off at very high concentration, and zero concentration there, slowly diffuses. That's high concentration to low concentration, right? It's this idea. Same thing happens here. Here you have high concentration of water molecules. Here, right? Low concentration of water molecules. So water starts moving. High concentration, low concentration. Salt tries to move, right, the other way, but it cannot because of the membrane. So then at the end, what happens is that you get equal concentration of water on both sides. My mistake. It doesn't happen because salt doesn't go this way. So you get essentially water going up here, until this cannot go anymore, right? It fills up. Of course, that's not what we are looking for. You want the opposite, right? You want to take the water out of the salty solution. So you want to do the opposite, and this is referred to as reverse osmosis. In order to do the opposite, all you have to do is push down here, right? I can push down here really hard, such that I can push the water molecules through the membrane, but not the salt. The salt is too big. It cannot go through the membrane. It gets trapped. But the water can go through. So I push until I get clean water. That's reverse osmosis. Okay? So the key thing to keep in mind here is that reverse osmosis requires huge amounts of energy to push the water through the membrane. That's the big disadvantage. It's not easy, right? You can imagine if you want to push huge amounts of water through a membrane that cleans this really small particles of salt. It requires a lot of pressure, right? A lot of energy to go through it. And that's the problem. So these things, this water that's generated by this turns out to be very, very expensive. So unless you can subsidize it because of public policy, or you can somehow, if you're Saudi Arabia, your energy is actually less expensive than water, then you don't care. Or, you need to come up with other solutions, which is where we come in. Could we start thinking of using sunlight to do this, and to generate this energy? So the obvious thing is simple, right? You just use PV. You use solar panels to essentially push this through, which is the first example we'll see. So this is an example which was demonstrated. So I'll point out the key complications here, because the full system design is also a useful example to think about when you think about your project. Okay, so this is again, photovoltaics is being used as a primary energy source for reverse osmosis. The system is simple. You have solar panels here. Okay, there's some control electronics which includes a tracking system, so it tracks the sun. There's a desalination pump, so the solar panels are essentially running a motor on a pump, right, pushing the water through. You have a desalination system which usually has a series of filters, so it's not just a single membrane, it's a series of membranes in general. And then the clean water gets pumped into a water storage tank. Simple, right? Now, one very important complication is the fact that most pumps, let me ask you, I think everyone has seen pumps, right? Pumping water somewhere, or pumping something, oil, whatever. I assume you've never seen pumps that's stop and start all the time. They're almost always constant, right? Almost run constant. And there's a very good reason for this. Pumps are designed, and this both electronics and mechanical, such that you want to have a constant velocity. That gives you the highest efficiency. You can actually prove this theoretically. Okay? These things are basically little blades. So you don't want blade to stop, or go fast, slow, fast, slow. Right? You want to go at a constant speed, which is problematic with this. Why? Because you have sun, which is very bright, suddenly a cloud passes by. So your electricity drops. The output from your PV drops. And that's a problem, right? Your motor expects some current, suddenly drops, it cannot turn. And that's the big problem that they solved here. So let me show you the example. Show you this example. So this is an example system which was installed at MIT on one of the rooftops. And you can see this is solar radiation, which is, of course, varying with the sun, with the clouds and so on. And this is being tracked. And you can see the water is being pumped in here. They colored the water with blue dye, so you can actually see this in this particular example. But what the key innovation here was that they built the control electronics with a battery pack to ensure that what comes out into the pump is relatively stable, even though you have these huge variations from the sun. Okay, very important innovation. Right? Well, it's relatively simple, but an important problem that they try to solve. Again, a good example of the sort of thing that I want you to start thinking about for your project. Now, this sort of things is useful for portable disaster relief. Again, it's an optimal control problem. It raises an interesting question which we want to spend huge time on. Can optical engineering help here? You don't have to answer it, but something to think about. I think it can. Obviously, you can do things to the solar panels to have them either be more efficient or generate more consistent power and things like that. But we'll talk some of this in this class, but not right now. Okay, so going back to something less high-tech is what's referred to as salinity gradient solar pumps. So these are very, very simple, but very interesting systems to understand. So let's see what it is. So you have the sun, and then you have a little pond here. And the way it works is the following. The top, you end up with low salt content, because the salt essentially sinks, right? It's heavier. So at the top, you have this low salt content cool water. In between, you have what can be thought as a salt gradient layer, which maintains this concentration gradient, and because of gravity versus diffusion, as you can imagine. And then you have high salt content hot brine at the bottom. Now, the denser, saltier water heats up at the bottom. The salt heats up, absorbs heat more than water. So the water that's saltier will get more hot. Okay? So on the top you have cool water, bottom you have hot water. The middle layer sort of acts like an insulator. Top layer remains cool. So this situation where you have one side that's hot, another side that's cold, with some connection in between. I'm pretty sure you've seen this in your freshman physics class. Okay? If you haven't, this is nothing but what's referred to as a heat engine. Okay? And we'll talk more and more about this along the way. In fact, all solar cells can be thought of this way. That's the sun, very hot. That's your solar panel, very cold. It's exchanging energy between them. Thermodynamically, they're identical to what we're talking about here. Although what we're talking about here physically does something quite different. Okay? This is a heat engine, means that it can do work. It can be used to do something. And the way you do something, it can vary, and we'll see many, many examples of it. But this is kind of a common theme in this class. So hot side, cold side, the heat engine will do some work by making use of that. Okay? And it's exactly what happens here. And you can see what happens here. So essentially what happens here is that the hot brine, in this case, gets pumped in. So you have a little pump that runs here, which is shown right there. It pumps in, and you essentially heat up an organic working fluid, like a fluid that you have in your refrigerator. And we'll talk more about that. But some kind of fluid. Okay. And that fluid gets hot. It runs a turbine. Okay, it's hot, moves a turbine. Generates electricity right there. Okay, and then it passes into a condenser where it cools. Okay, so it kind of condenses from the gas, it becomes liquid and goes. So here, when it gets hot, it becomes gas. I forgot to mention that. So it's a liquid here, it becomes gas, then it cools. After it has pushed the turbine, it has lost energy, and it can cool and become liquid again, and it falls back down and in this pump, and the whole process repeats. Okay, and this cold water here, of course, cools the condenser. So that's the cold part. So again, it's a common theme. Hot part creates a gas that runs a turbine and goes to the cold part, loses its heat, and then repeats. Okay, this is what's referred to in thermodynamics. We'll come to it as a Carnot cycle. As I said in the last class, even though this is an optics class ostensibly, we need to really understand some thermodynamics to really make use of that. Okay, we'll talk more about this in one of the lectures on thermodynamics, but keep that concept in mind when you think about these systems. So what, again, just to read what I just said, it produces low grade, less than 100 degrees Celsius because of the sun, thermal energy, which is useful for heating, some electricity production. So there are examples of these systems, for instance, in cold places like Iceland and so on, where they actually, I think it's Iceland, or maybe it's Norway, I can't remember, where they actually pump these kinds of moderately warm water into homes for heating and things like that. Because you don't need your home to be super hot. Just, if you have a good insulated home, you just need a little bit of moderate heat. Of course, the efficiency is pretty low, 10%, 15%. You can imagine why, right? Because, of course, these things are not great absorbers of sunlight. They just absorb only the thermal radiation, not necessarily visible light or UV light. So the amount of energy that you absorb is already very low. And then, of course, you have the efficiency of the whole system here, which you have to multiply, and we'll talk more about that later. The one advantage, which we will come to again, is in the future is direct and diffuse sunlight is absorbed. What does that mean? Kind of a term, first time we are encountering. Direct sunlight refers to what we see out today. There are no clouds. Okay, and the way to know that is it will form nice sharp shadows. Okay, diffuse sunlight is what looks like this. You can put up your hand under the cloud and you'll see a blurry shadow. Somewhat blurry. If you get closer, it'll be sharper, but further away. Okay, that's diffuse. And the difference, the way to think about it, if you have direct sunlight, the rays of light are going all parallel to each other. It's going straight, let's say. If you have diffuse light because of clouds or scattering and so on, the rays are all over the place. In general, it's much harder to collect diffuse sunlight, as you can imagine. Much easier to collect direct sunlight. And we'll come back to this again. It's the first time we'll encounter it, yeah?
So, coal, natural gas, nuclear power plants all work off of the heat engine.
Yes, exactly. Everything does. Yes, absolutely.
So does, I don't know what it's called, but the solar power plants where they have all the mirrors.
Yes, exactly. We'll talk about those as well. Yes, that's right.
I was just wondering why they don't combine those. If they're heating it up, obviously the salt is staying down. So why couldn't they just use that water and pump it out for potable use?
You mean, sorry, I didn't quite get you. You mean for the nuclear power plants or something? What happens to the hot water?
No, in this case, for the solar power plants, they use all the mirrors to heat up the
Yes,
tank.
yeah.
So then we're using solar.
Yeah.
But that water turns to steam, goes through the turbine,
Yeah.
it generates the power. Then that water, which now has no salt, you put salt water to begin with. And that water that now has no salt
Can be used for drinking. Yes, that's correct. Sorry, I forgot to mention that. You're absolutely right. So in this particular case, of course, they're not using this water for drinking the way it has drawn it, but you're absolutely right. You could take that. Then it becomes not a closed system, so you can do that with an ocean and so on, where you have an infinite supply. Yes, absolutely right. In fact, I think it's the next example is something like this.
Oh, okay.
Yeah, it's a good observation.
Just trying to wait, but I thought you were moving on, so that's why.
No, very good. That's a good observation. Absolutely. Oh, actually, it's coming. So this is similar to what you're talking about, but what you're talking about is coming later on. So this is something, by the way, fairly common, I would say, in the Southwest. I've seen something like this in southern Utah. Pretty straightforward. You essentially have a parabolic trough collector. So these are big panels of parabola. So it's a one-dimensional, it's a two-dimensional parabola. The third dimension is the same, right? It's uniform. And this is related to the fact that the sun is moving in that axis. So this is not a great picture with the sun right there, but the idea is that the sun axis is now parallel to this focus of the parabola, the focal line, right? So you don't only need to track the sun in the other axis, which is why this only has a tracker which goes like that, not the other way. So the way it works is simple. So you have sunlight coming in, it gets focused to this line right there, and which is right here. And a fluid passes through here, which can be water, for instance, and you can create steam and use that for drinking. Typically, by the way, these things are not used for desalination, as far as I know, because salt tends to corrode these pipes, so it's not a great thing to do. Typically, these things are used for electricity generation, which we'll come back to. So the idea is that heat transfer fluid can be used for high-grade thermal energy or electricity production or thermal distillation, which is desalination. Tracking is, of course, required. It's relatively expensive. So this is related to what you were mentioning before. So this is the same as before, where we had this natural salinity gradient still. Upon here we have what's called a single effect solar still. Still just refers to the fact that it's still water. It's just a pond. Okay. So here we have a pond with which is like a greenhouse essentially. So you have a transparent glass cover on the top, a reflector like your solar cooker, and it's just one-dimensional, so you see this, it's extending in that direction, and some support structure. And what happens is that the water, dirty water comes in through this inlet, okay, it gets heated up, and it rises, it condenses on the glass cover, and it flows down, basically, down to here, and you get fresh water coming out. Very simple system. And then you can use the water for drinking, as you'll find out. In this case, it's not a heat engine. I mean, it's not a heat engine to generate electricity. Of course, it's a form of heat engine as well, because that's your hot area and that's your cold area. It's simple, inexpensive, but slow and useful for small amounts of water. So, for example, the energy to evaporate 1 kilogram of water at 30 degrees Celsius is about 2.4 times 10 to the power of 6 joules, so 2.4 million joules. So let's all do a quick example problem here. I'm going to turn on the light because I want you to, you can do it in your head if you want to, right? But one of the things I want you to be able to do is have a good sense of units. Watts, joules, seconds, meters squared. I know some of this is very basic, but it's very easy to get confused. So it's good to kind of review ourselves on this. The second thing I want you to do is be able to think in orders of magnitude. Now, do I need 1 million joules or do I need 100,000 joules? I don't really care if it's 2.6, 3.5, who cares? I want you to be able to think in orders of magnitude because this will become important in your design. So that's the question. Let's see if you can do it. Solar insolation is 250 watts per meter squared. So, I have to define what insolation is. So insolation is the power density of sunlight, and we'll keep talking about this. So you hear this many times. That's what it's called, insolation with an O. It's in units of watts per meter squared. Watts is, of course, what? Joules per second, right? The rate of doing work. So let's remind ourselves what these things are. Joules is energy, right? Watts is power. Yeah, I think those are the only two things we need to think about. And power is the rate of use of energy, right? So watts is joules per second. And that should be enough for you to answer this question. That's what I mean by understanding units. Very simple, but important to kind of have a good handle on it. So if the insulation is 250 watts per meter squared, how much water can be produced per unit area per unit time? And I've given you the energy to evaporate 1 kilogram of water up here. And let's assume it's 30 degrees Celsius. I'll let you think about it for a minute. Okay, so we need 2.4 million joules for 1 kilogram of water. And we know coming down from the sun we have 250 joules every second, every meter squared. So the question is, how many kilograms of water can we get per meter squared of area of collection, right? So how would anyone want to volunteer? I think some of you did. No? Anyone?
Isn't it just 250 divided by
Yes.
1.1?
Right. So again, just think. I want you to get a feeling for these things rather than doing the math. I don't care dividing. So, and we need to understand the orders of magnitude. So we'll do that too. So it's just that this is what's coming per second per unit area, right? That's what I have coming in. And this is what I need, right? 2.4 million joules per every kilogram. So how many kilograms can I get per unit area? I just divide them. And this, I'm going to get rid of this. Approximately it's 100. So it becomes 10 to the minus 4.
About 0.375 an hour. Not bad.
Oh, per second too. Sorry, yeah, I forgot the second. Right. Not a lot, no? How much? Sorry, how much per hour? What would you say?
0.375 kilograms.
So 375 grams.
Yeah.
A meter squared is pretty big, so yeah, I guess it's not too bad. Now, first of all, before we go on, everyone okay with the concepts, right? So you have this much energy coming in, this is what you need to do, and this is, like relatively simple. Also important the units, so make sure you're fairly comfortable with the units, and you will get as we move on. The important thing here is the number. So the number is relatively small, 375 grams. It's not a lot. Roughly the density is a gram per ml, right? So 375 ml. Yeah, it's not too bad. Per meter square for an hour, so it's relatively slow. The one thing we haven't considered here is efficiency. We have assumed it's 100%. Whatever thing we're using is 100% efficient, which is never true. So we have to account for that, and typical number of efficiencies put there is 30 to 40%. That's a good system. So you have to scale everything by that number, divided by, you need 10% more, or divided by 1.3, right, to figure out how much energy you need. So again, that's what I mean by understand the scale of the problem. So in other words, is that enough water to support a household? Is that enough to support a village? One person? What is it? Right? And that's the sort of thing you should start thinking also from a scale point of view. That's what I want. And it could be electricity. Here we're talking about water, but imagine the same kind of situation. The material selection, of course, is very important, and many system design improvements are feasible. So I hope one of the teams will think about this, and not this particular thing, but the problem of water usage, let's say. Okay, another example is the still with the greenhouse combination. So it's very similar to what we just talked about. So I won't spend a lot of time on it, but the idea is the fact that you have an inlet of water here, essentially a little surface, and it gets heated up. Because it's a greenhouse, it gets heated up more efficiently because you're trapping the heat, the long wavelengths as we talked about. The water forms vapor and condenses on the cold roof at the top and gets collected here where you can gas it out. So we don't need to know this too much. By the way, we don't need to necessarily know all the details of all these things. My goal here for this lecture, anyway, I'll point out where it's important for your quiz and stuff, is for you to think about how you will approach your project problem. That's my goal here. Okay? I'll point out where it's important for exam. I don't really care. I'm not a mechanical engineer, so I don't care about the details of this. But big questions like what's the big challenge here? You have corrosion of the collector due to contacts and all that. Those things are important. We should keep in mind. Okay, to summarize, we have two ways of solar desalination. One is direct and one is indirect. Direct means you essentially create solar to create distillate. Either you heat up, form gas and collect it, or you use small scale stills, etc. So directly using the heat of the sun to clean the water. Indirect means you use sunlight to produce energy, electricity, and then use that to clean the water. Okay? They're both good. Both have their own purposes. So solar to produce energy used in separate system for distillate, solar thermal or photovoltaics. Now solar thermal is a form of direct, so I will actually put it on the other side. Now there are also applications in humidification, dehumidification, which is very important here for us in Utah. And there are lots of very interesting systems which we don't have time to go into, but just be aware that there's lots and lots of things that already exist. There are relatively big industries out there already which deal with this. So hopefully some teams will start looking into this. Okay, now let's talk about the next, I would consider even more difficult problem, which is the problem of solar refrigeration. Right? Most of us know, living in the desert, that cooling is one of the biggest reasons our electricity bills are high. So we consume a lot of electricity. So can we do something about that, right? It's not just to save money, but also potentially to reduce carbon emissions and so on. So, and it can also be used to keep foods, medicines cold, in remote situations, if you're hiking, camping, whatever. Could you make ice, for instance? So first of all, let's try to understand what this is. What is refrigeration in the traditional sense, right? And let me point out, it is also a heat engine, first and foremost. Hot and cold sides. So let's look at a very simple introduction first. Now point out the key things.
The working fluid is sometimes a gas, and I've designated that by red.
So before
a liquid, and I've designated that by.
So before I move on here, this is a refrigerator in your house. Let's say it has a tube here which collects the fluid which moves around. So the red is gas. You have a compressor, okay, and the blue is colder. It's a liquid. So you have a cold side and a hot side, as you will see. Okay, so just see very, very quickly what happens here.
By blue. So what happens? Well, there's a compressor. The compressor is a pump that pressurizes the working fluid and pumps it around in this loop. And so when the compressor gets a hold of the working fluid, it compresses it and it becomes a high-pressure gas. And then that fluid moves through some coils, sometimes in the bottom of the refrigerator, which is actually a rather poor place for it energy efficiency-wise. Better places on top. And you may have seen ancient refrigerators that actually have a little round thing on top, and that was a better place to put these coils. Sometimes in the back, sometimes in the bottom. But the purpose of those coils is to take that high pressure gas and let it get rid of some of its energy, in the process condensing to a liquid. So as it goes through those coils, it gets rid of some of its energy, it rejects that energy to the outside environment, the room the refrigerator is in. Translation, if you touch the coils of the refrigerator, either underneath or back, they're warm. They're giving heat out to the room that the refrigerator is in. The refrigerator, ironically, gives off heat. Well, not so ironically. We'll see why in a minute. Okay, so now we have the working fluid in liquid form, but still at high pressure. It's rejected this heat to the surrounding environment. Then it moves through the expansion valve, and the high pressure liquid going through this valve, which is basically just a tiny hole, it's a tiny little orifice where the gas is forced to go through, and as it goes through, it expands, cools, and becomes a low pressure liquid. So now we have low pressure liquid, and the low pressure liquid is then circulated through a series of coils that are insulated from the outside environment, but they're in contact with the innards of the refrigerator. And heat flows, again, that's the right term because heat is energy flowing because of a temperature difference. Heat flows into these cool coils, and it evaporates the liquid, and it takes energy to evaporate the liquid, and that energy is ultimately extracted from the materials inside the refrigerator. It goes into the working fluid, it's pumped around, the heat has been extracted from the contents of the refrigerator, and now the working fluid is a gas because it's evaporated at the expense of the energy of the things inside the refrigerator, and it goes back to the compressor, and the cycle starts over again. The net effect of the refrigerator is simply to pump heat from inside the refrigerator, from the contents to the outside.
Okay, so we see that. Again, you had a cold area and a hot area, and you're taking, and you're, in this case, you're creating that by essentially taking energy from the cold area and putting it into the hot area. So yeah, cold and hot. Again, it's a heat engine. Okay? So, so now you understand, hopefully, the basic idea of how you're cooling something inside a refrigerator. One obvious thing you can imagine doing is to make this, let's say, solar powered, is to just apply PV. Right? You can use solar panels to essentially run this. We'll talk about more interesting things, but so that's solar electric refrigeration. So you essentially have a solar panel which is doing some work here. The sunlight intensity multiplied by the area of the solar panel is the input. Okay, that's a heat input. It runs a DC motor. Of course, you need to be careful with the controls here, as we talked about. No motor likes to go on and off, on and off, on and off. Right? You want to have some uniform constant running. So you have to be careful with the electronics here, which runs the compressor, of course. And then you have which evaporates the liquid, which grabs the heat from the contents of the refrigerator. So that's a cold area. And then it runs through here, condenses here, and dumps the heat in the hot area outside. Okay, and then cycle runs. Now, what are the key challenges here? You know, if you grid connection, battery or variable capacity compressor needed. Like I said before, the capacity of the compressor should try to be stable, or you need to have a very expensive compressor. Efficiencies can be about 30%, but it's relatively expensive because of the solar panels and the fact that you might need some fancy electronics or compressors. Okay. There are other options as well, which we won't talk too much about: Stirling cooling, thermoacoustic cooling, magnetic cooling. But I want to talk about one particular type of cooling which is very interesting, not necessarily related directly to solar, but something you should know about, especially for those of you who have taken some semiconductor devices or physics classes. It's referred to as thermoelectric cooling, because you can actually buy devices like this on the market. You can buy coolers. Sorry? Yeah, TC, yeah. So this is also called a Peltier device because it's named after Peltier, who discovered the effect. And the idea is relatively simple. So you basically have a PN junction, okay, so a semiconductor device with a P-type semiconductor and type semiconductor. All that means is that you have a semiconductor which is highly conductive with electrons or highly conductive with holes. Holes are essentially absence of electrons. It's okay if you don't really understand what those things mean, but we'll see from a context what it means. So you apply a DC power source, okay, so that's your battery, negative terminal is here, which means that current is flowing this way, right? Current is flowing this way because of that, right? Ignore what's on the top, just imagine. So that's the circle. If the current is flowing this way, the electrons are flowing the opposite way. Right? Electrons are always flowing the opposite way. Current, so electrons going out, and going into this junction. So here. Okay? It's going that way from this side to that side. Now what's interesting is that electrons carry heat. They can carry heat. They're good conductors of heat. So in this particular case, the heat will be absorbed on this side and transmitted to the other side and released there because you have a heat sink right there. So this side becomes hot and this side becomes cold. And the same thing happens on this side. The holes go in that direction because the electrons are going the other way. You can think about them as holes going that way. There's a fundamental difference between the hole and the electron, which you don't have time to go into. One is because the electrons that we're showing here in the conduction band, they can conduct heat, whereas the electrons which are responsible for the holes here in the valence band, they cannot conduct heat. Anyway, that's not so important for us. Just imagine, essentially, that electrons and holes are simply taking heat from one side and dumping it on the other side, purely by passing a current. So you have a device, by simply passing a current, you can cool. There's no compressor, no liquid, no fluid, so it's pretty nice, right? This is what they use on spacecrafts in International Space Station, exactly because of that. The big problems with this, it's super expensive, but you don't care if you're sending something to space. It's very portable and small. That's the main reason why they use it in space, because weight is the most expensive, biggest concern when you send something to space. You want to make it as light as possible. Like relatively low efficiency and quite expensive because of these materials. You have bismuth telluride, all kinds of exotic stuff.
What are you talking about?
So bismuth telluride, I don't know the exact numbers, but I'm going to guess it's about 1,000 to 10,000 times more expensive than silicon. So the material itself, yeah, I don't actually remember what the.
Because I know there's inexpensive types that you can get for $10.
They're probably really small or really not.
You should tell NASA.
It's about 40 by 40.
Yeah, I'm not familiar with them, but yeah.
That you can find them on
eBay,
Amazon. So
I don't know what the performance is, but I'm going to guess they're not as good as what. I mean, in the case of
not as good as NASA.
yeah, you probably in the case of NASA, what they're trying to do typically is not necessarily trying to cool something to super low temperatures because the space is already very cold, but you're trying to maintain temperature. So you have an International Space Station, for example, can get hot because you get lots of sunlight coming in, like a greenhouse, right? So you want to kind of cool it, and you cannot cool it by simply taking advantage of the fact that it's vacuum in space. It's not easy to radiate things out, so you have to have some kind of a cooling mechanism. As I understand it, they use some version of chip. That's a good point. I'm not sure. You cannot. What's even more interesting for me is could we bypass electricity altogether? So what we've talked about so far is we've taken sunlight, turned it into electricity, and used it to cool something. Could we just bypass that step? Right? That's kind of interesting. And it turns out it's possible, but it's hard. It's complicated. As an example, so could we use solar heat rather than electricity? So in this example, again, the idea is simple. You have a hot and a cold area. That if you can create that, then you can run a heat engine and do cooling. That's it. So in this case, you have a glass cover and you have these rods running some fluid in a channel. Okay, and you have an absorber plate just to heat up. So you have sunlight which heats up this fluid. Cold, let's say water. Cold water comes in, gets heat up, goes out as hot water. So this is a cross section of the channel. So that's the glass cover. Then some kind of absorber plate right there, insulation top and bottom, and then you have fluid going through. Now, once you have cold and hot, water, then you can run a heat engine essentially as a compressor, just like as we were talking about in the compressor. It's not shown here, but imagine the hot water going, touching or getting close to the fluid that is the cooling fluid, and that evaporates. Right, takes the energy, evaporates. And then it can condense on the cold side. So then you can start cooling. So you can do that instead of running a compressor. And this is just a slightly different design where you have individual insulations, individual absorbers in each tube. Won't need to go into much detail there. But so heat is input to the engine for cooling. Challenges collector loses more heat at higher temperatures. We'll talk more about this later on, so not so important. This is an important concept we will come to again. The cooling heat engines in general work better when the temperature difference between the hot and the cold regions are very large. But if you make them very large in this context, you start increasing losses. So it's a big problem as well. Okay, so that's my last slide because I wanted to leave about 5 minutes to talk a little more about the projects. So I think we talked about this, but just to review. So September 28th is our first presentation, which is, the idea is that I'm going to, if you told me something you're excited about, I'll assign that as your topic, but if you haven't told me, I'm going to assign some topic to you, first of all, and the idea is that I want you to go and figure out what is being done today on that. As I said, what are the solutions today? What are the problems with those solutions? So pros, cons, comparisons, overview of the existing technologies, and that's the first part of it. And I'm going to give that as an assignment, as one of those periodic assignments. I'll post it on the website, probably next week, after we have the teams and all that. After that, then you have your innovation. Like, what is the problem that you try to solve? What is the innovation? Try to be creative there, take risks, and then you present